So the next topic is going to be Pythagorean identities. And if we talk about the triangle in quadrant 1 for our unit circle, we discussed that cosine is the adjacent side, sine is the opposite side, and we can also rewrite these as x and y. So this particular triangle will have a hypotenuse or radius of 1, which is why we can call it the unit circle. So if I use the Pythagorean theorem for this particular triangle, we'll have x squared plus y squared is equal to 1 squared, which just reduces to x squared plus y squared equals 1. Now, because x is equal to cosine and y is equal to sine, we can rewrite these as cosine squared theta plus sine squared theta is equal to 1. And this is the first Pythagorean identity. First of three. So the first one that you will want to memorize is cosine squared theta plus sine squared theta is equal to 1. Now, to get the other two, there's three main Pythagorean identities, but to get to other two, you only need to memorize this first one. So the second one includes tangent and secant, and we can get to that if we just divide this entire equation by cosine. So divide cosine squared theta into cosine squared theta, and then sine squared theta divided by cosine squared theta, and then 1 divided by cosine squared theta. Cosine squared divided by cosine squared will be 1. Sine squared divided by cosine squared, that's going to be tangent squared. And then 1 over cosine squared is going to be secant squared. And this is your second Pythagorean identity. We'll use the same approach that we did with cosine for the third one, but instead of dividing by cosine, you can now divide by sine. So we'll have our original Pythagorean identity, and then instead of dividing by cosine, we'll divide by sine squared. So cosine squared divided by sine squared will be cotangent squared theta. Sine divided by sine is 1, and then 1 divided by sine squared is going to be cosecant squared theta. And then this is your third Pythagorean identity. So people typically get nervous about this because they're like, I have to memorize all of these? No, you only have to memorize the first one. And then from there, you can divide by cosine, divide by sine, and you can get the other two from there. Now, in class, we talked about things called corollaries. And corollaries just means there's a correlation. It means it will be the same, but it could be slightly different. And that just means we're moving things around. So the first corollary is going to be sine squared theta is equal to 1 minus cosine squared theta. So if you look at your first identity, all I did was subtract cosine from both sides. And then we can also do the same for cosine squared. We'll have cosine squared is equal to 1 minus sine squared theta. We can also do this with the second and the third Pythagorean identity. So we could have tan squared theta is equal to secant squared theta minus 1. So all I did was subtract 1 from both sides. And then we can also have 1 is equal to secant squared theta minus tangent squared theta. And that's when I subtract tan. The last two will be from the third one. If we subtract cotangent from both sides, I get 1 equals cosecant squared theta minus cotangent squared theta. Or we can get cotangent squared theta is equal to cosecant squared theta minus 1. So these are just 6 of the possible corollaries. We can also multiply everything by -1, which will also create an equivalency for these. But again, the main one that you have to remember is this one, because we can derive all of the other Pythagorean identities and corollaries just from that one. All right, so now what are you going to be expected to do? It says from the equations above, find a single trig expression equal to the given expressions. So right now we have 1 minus cosine squared. You only know the reciprocal in Pythagorean identities, and this is going to be a Pythagorean identity. So you should immediately think of sine squared x plus cosine squared x is equal to 1. Now the form has changed a little bit because we're dealing with a corollary. So if I subtract cosine from both sides here, I am left with just sine squared isolated, so we get sine squared x. And now if you're in an assessment situation, I already wrote this once. Just don't rewrite things. You can just flip back to it and find it, so that's why I bubbled it. So try not to do multiple things if you don't need to. Same thing here with b. I have 1 minus sine squared. I already wrote the original Pythagorean identity. If I were to look at this again, and I were to subtract sine squared from both sides, I end up with just cosine squared x. So this one is going to be equal to cosine squared x. Now we're seeing a different trig expression. I see secant. Go ahead and get used to tangent x and secant x. They're going to be besties. They're always together. They're going to be together in this unit and for the rest of the year, and they're also together for almost every single identity in calculus, including differentiation and integration. If you don't know what those mean, that's okay. So if I think back, I might not remember this one. I'm going to be honest, I don't, because I always just resort back to this. I'm looking for secant, so I need 1 over cosine. So I'm going to divide everything by cosine squared x. So that means I have 1 plus tangent squared x is equal to secant squared x. So I already wrote this once, which means I'm going to bubble it, and so I can come back to it if I need it. And because I have secant minus 1, if I subtract 1 from both sides, I'm only left with tangent squared x. So this is tangent squared x. So I expect your papers to be a little messy, like on the sides, but whenever you're showing your work, make sure it's orderly. All right, next we have 1 minus secant squared. So I'm going to flip back to my Pythagorean identity that has tangent and secant. I have 1 plus tangent squared is equal to secant squared. So just so I don't scroll back and forth, I'm going to rewrite that. 1 plus tangent squared is equal to secant squared. And I specifically want negative secant squared, so I'm going to switch these two. So I get 1 minus secant squared x is equal to negative tangent squared x. And then I'm going to box that as well. This is technically a corollary, even though we didn't write it on the previous page, but it stems from that same Pythagorean identity, and we're just moving some terms around. So this is negative tangent squared x. All right, now we have negative cotangent squared x minus 1. I can tell this is another Pythagorean identity because I have a squared, and then I have a constant of 1. So I know this is going to be, it's cotangent, its bestie is going to be cosecant. Same thing, when you get to calculus, you're going to see these two together all the time. So I'm going to revisit my original Pythagorean identity. I don't like it, but you'll see this referred to as the granddaddy if you look things up online, because you can get any of these identities, Pythagorean identities, if you start from here. So now that I need cotangent, I know cotangent is going to be cosine over sine, so I'm going to divide everything by sine. So that means my first term is cotangent squared x plus 1 is equal to cosecant squared x. And then I might need this later, so I'm going to go ahead and bubble it. Now if I look at this, I have a negative and a negative, but my identity is positive. So I'm going to go ahead and factor out that negative 1. So I'm left with cotangent squared x plus 1. And now I can see that I have my original identity, but now it's just going to be negated. So I'll have negative cosecant squared x, or you can just rewrite it as negative cosecant squared x. And I'm showing every step. You won't have to. As you get more comfortable with these identities, sometimes you might just go straight to this one. But if you're still getting used to it, I would continue to explore every single step. All right, now we're getting a little bit more complex. We have 1 minus secant theta times 1 plus secant theta divided by tan theta to the power of 4. This is going to be a difference of squares. except we see the expanded version right now, and we want to rewrite it as a condensed version. So I feel like I don't remember that. If you have a minus b times a plus b, that will reduce to a squared minus b squared, okay? So in this case, my a is going to be the 1, my b is secant theta. So I can rewrite this as 1 minus secant squared theta divided by tan fourth theta, or tan theta raised to the 4th. Also, if you just double distribute, 1 times 1 is 1. 1 times secant theta is secant theta. Negative secant theta times 1 is minus secant theta. And then negative secant theta times secant theta is negative secant squared theta. And then difference of squares, the middle terms always cancel out. All right, so that was an Algebra 2 review. Now we're going to need to resort to our identities because we need to reduce this to one single trig expression. So I wrote secant squared somewhere. It was up here. So I have my second Pythagorean identity here, but I specifically want 1 minus secant squared. I actually did it over here. There it is. So again, that's why I bubbled this, because now if I want 1 minus secant squared, I can rewrite that as negative tangent squared. Divided by tangent to the 4th. All right, so this is another Algebra 2 review. If I have x squared divided by x to the 4th, properties of exponents, that will reduce to 1 divided by x squared. We can do the same thing with our trig expressions. So if we have 2 tangents in the top and I have 4 in the bottom, that means I will have 2 more left in the denominator. So they'll cancel out. All right, when we write it as a single trig expression, we do not want to stay in a fraction, right? We have our reciprocal identities to change that. The reciprocal of tangent is cotangent, so I'm going to rewrite it as negative cotangent squared theta. So it should always be a single trig expression, not written as a fraction. All right, simplify using identities. So again, we are simplifying down to one single trig expression. Tangent theta, cosecant theta. So if you're not quite used to these identities yet, I would rewrite them as cosine and sine. That way you can see what cancels out and can reduce it from there. So tangent theta is going to be sine theta over cosine theta. Cosecant theta is going to be 1 over sine theta. Again, some of you already recognize that the sines would cancel out. You can skip this intermediate step, but it might help if you have like 3 minutes left on an assessment and you're stressing out. You don't want to make any silly mistakes. So the sine thetas will cancel out. So we're left with 1 over cosine theta. We can use a reciprocal identity. So we're left with secant theta. All right. Sine squared theta plus tan squared theta plus cosine squared theta. So we have a bunch of squares, which means hopefully there's a red flag going off. This is definitely going to be Pythagorean identities. Pythagorean IDs. All right, so if you see a bunch of squares, you want to try and think of that, the granddaddy one, which is sine squared plus cosine squared, which I do see that one. So sine squared plus sine squared theta plus cosine squared theta is equal to 1. And then we just have that plus tangent squared theta. This is going to be another Pythagorean identity, so I'm going to scroll up. I already did it once. 1 plus tan squared theta is going to be secant squared theta. So I can rewrite this as secant squared theta. And even though it's squared, it's still technically a single trig expression, so we're good. All right, next we have tan theta divided by secant theta. Whenever we're dealing with a fraction and you can't easily see how to manipulate it, I would separate the two. So I have tan theta times 1 over secant theta. Some of you, your first step might be to rewrite that as cosine, and that's okay. So you would end up with tan theta times cosine theta. So tan theta can be rewritten as sine theta divided by cosine theta, and then secant theta, or 1 over secant theta, is just cosine theta. And if we look at this, the cosines cancel out. So we're left with sine theta. And this is a good example. Well, these last three are actually good examples. We have these complex, well, not really complex, but we have multiple terms or we have multiple things happening, but we're able to simplify them so that they're easier to evaluate and or manipulate for later uses. All right, 1 minus sine squared x divided by cosine x. So hopefully as we go through more of these, you're starting to see that that's another Pythagorean ID. That's going to be your original one, but it's a corollary. So I did this one up top. Yep, so we had 1 minus sine squared here, and that's equal to cosine squared. So we'll have the numerator be cosine squared x divided by cosine x. And we've already seen this. We have 2 cosines in the numerator, 1 cosine in the denominator. So if I have x squared divided by x, properties of exponents, that's x to the 2 minus 1, so we just have 1x left, or in this case, just cosine x. All right, here's another one with multiple terms. Secant squared x minus cosine squared x minus sine squared x. So there is a corollary in here. Kind of, it's just multiplying everything by -1, but I see my cosine and I see my sine. However, I would like these to be a plus. I need cosine squared x plus sine squared x to equal 1. So in this case, because we're not dealing with an equation, I'm going to factor out a -1, which means they both become positive. You don't have to show this step if you're just like, oh, it equals -1, because it's like you're multiplying the entire identity by -1. You can just rewrite it as -1. So we'll have secant squared minus all of this here becomes +1. So just to get rid of the parentheses, we have secant squared minus 1. I feel like I did this somewhere. I think it was up here. Nope, that's 1 minus secant squared minus 1. Or maybe I didn't do it yet. There's so many I forget sometimes. Okay, but I know I used it here. So if I come back to here, secant squared minus 1, if I subtract 1 from both sides, I end up with just tan squared. Oh, it was a corollary, that's why. So it was here. That's where I remember it. But if you see me, I'm going back and forth between all the problems because I want to find commonalities. That way you're not redoing everything all the time. So the further you get into your ICAs or homeworks or assessments, continue to scroll back so that you can pull from what you already did. And lastly, we have secant theta divided by cosecant theta. If you're not comfortable with these identities yet, I would split up the fraction. So we have secant theta times 1 over cosecant theta. Or something that I noticed was some people would rewrite it like this. Secant theta is the same as 1 over cosine theta. 1 over cosecant theta is the same as sine theta. So that's okay, you can do that. So again, secant theta can be rewritten as 1 over cosine theta. 1 over cosecant theta can be rewritten as sine theta. So now we're back to where we were here. Sine divided by cosine is just tangent theta. All right, so that's evaluating and simplifying to one trig expression. Next, we're going to talk about verifying. So this is the only time that you will see equations presented to you, and it's about verifying. Verifying just means you're going to manipulate one side. And you want to pick the side that has the most things to play with, or the most stuff to move around. So in this case, if we look at part A, you should definitely manipulate this side, because if you want to start with this and then try and verify that it equals that, you're going to have a rough time with that. With this one, it's easier to condense rather than expand. So if I start with cotangent squared theta plus cosine squared theta plus sine squared theta, we see our favorite Pythagorean identity. That is going to be 1. So we have cotangent squared theta plus 1. And then cotangent squared theta plus 1, that is going to be one of your other identities. the original third one. That's going to be equal to cosecant squared theta. So cosecant squared theta is equal to cosecant squared theta. And I usually draw an arrow to like prevent myself from moving things side to side. So you're not taking the square roots of anything. You're not adding and subtracting terms from one side to the next. You can only work with one side. That's what verifying means. All right, cotangent theta minus tan theta divided by sine theta cosine theta is equal to cosecant squared theta minus secant squared theta. So this one, you should definitely choose this side. Usually it will be the left side. If you're starting with a fraction, that's going to be the side that's easier to manipulate to a non-fraction. And these will always be verifiable. So if you're like, I can't solve it, therefore it's not verifiable, that just means you messed up, okay? So go back and double check. All right, we have multiple terms here, but overall it is one fraction. And then on this side, I have two separate unique terms, okay? But what I notice is that I have two terms in the numerator, so we can go ahead and split this into two terms. So we'll have cotangent theta divided by sine theta cosine theta minus tangent theta divided by sine theta cosine theta. And you don't need to rewrite the right side. We're not manipulating it. So this is a property that you should or hopefully recall from rational equations in Algebra 2. If you have multiple terms in the numerator, you can divide them. You can separate them as long as you keep the denominator the same for all. Because if we went the other direction, we could combine them because they have a common denominator. All right, so now we're going to go back to rewriting everything in terms of cosine and sine. So cotangent is going to be cosine theta divided by sine theta all over sine theta cosine theta. No, I deleted the whole thing. That's fine. Minus tan theta will be sine theta divided by cosine theta divided by sine theta cosine theta. This is an intermediate step, but I like to show it because sometimes I'll throw things into the denominator and people are like, how did that get there? So we have cosine over sine in the numerator, which means this sine can technically be rewritten into the denominator, okay? Because this is technically cosine over sine times 1 over sine theta times cosine theta. So that sine can be rewritten in the denominator. So this first term can be rewritten as cosine theta divided by, I'm going to pull the sine theta from the numerator, and then I also have the sine and the cosine already in the denominator. We can do the same for the second term. This cosine can be rewritten to be in the denominator, so we have sine theta divided by cosine theta times sine theta times cosine theta. And this is what we want. We want things to cancel out. We need less things. We have too many. So the cosines over here cancel out, and then the sines over here cancel out. So now I have two sines that are being multiplied. So that'll be 1 over sine squared theta minus, I have two cosines being multiplied over here. That'll be 1 over cosine squared theta. And then we have our reciprocal identities. 1 over sine squared is just cosecant squared. And then 1 over cosine squared is just secant squared. And I believe that's where we were trying to get to. Let's see. Yep. And then just connect it. All right, the last problem for this lesson, we have tan squared x divided by 1 plus tan squared x is equal to sine squared x. Okay, so I have more terms over here. Well, it's one term, but within this term, we have a numerator and then 2 in the denominator. So there's more items to manipulate here. Tan squared x, we can't really do much here. We could rewrite it as a Pythagorean identity, but the goal is to get rid of these constants. I don't see a constant on my right side, so in verifying, I want to try and get rid of them. So I'm going to leave tan squared x alone. However, this is a Pythagorean identity. It's the second one, so that will be secant squared x. So I'm going to rewrite secant squared x, or 1 over secant squared x as cosine squared x. So tan squared x I'll keep the same. And then rewriting 1 over secant, I get cosine squared x. So now if you get stuck, rewrite every term in terms of cosine and sine. So sine squared x divided by cosine squared x times cosine squared x. The cosines cancel out, so we're left with sine squared x, which is equal to sine squared x. All right, next will be sum and difference identities. Hope this video helped.